The first presentation in the course will be a talk by Michal Drobot from Infinity Ward. This lecture covers a novel rendering pipeline used in Call of Duty Modern Warfare. It enables a highly customizable software-based variable rate shading, a method to render parts of the render target at a resolution matching image frequency. Michal Drobot is a principal rendering engineer at Infinity Ward, an Activision studio. Most recently, he worked on the rendering architecture of Call of Duty Modern Warfare and Call of Duty Infinite Warfare. Before that, he helped in designing and optimizing the 3D renderer in Far Cry 4 at Ubisoft Montreal. Prior to that, he worked at Guerrilla Games, designing and optimizing the rendering pipeline for the PlayStation 4 launch title Killzone Shadowfall. Michal specializes in rendering algorithms, render architectures, hardware architectures, and low level optimizations.
Hello, my name is Michał Drobot. I'm a principal rendering engineer at Infinity Ward Activision. Before I start, I would like to say that there were just so many people working on this project, amazing engineers I had a chance to work together with or brainstorm on so many different research and development projects. I would also to invite you to another presentation coming from Activision this SIGGRAPH, Pre-Computed Lighting Advances in Call of Duty Modern Warfare by Peter Pike Sloan and Ari Silvenoinen. Last but not least, I would like to extend my special thanks to Natalia Tatarchuk, who made this SIGGRAPH course possible. This talk will present null rendering technique, software-based variable rate shading, developed for Call of Duty Modern Warfare. Call of Duty Modern Warfare is a 60Hz forward-plus rendered first-person shooter. During the game, players visit various locations ranging from close-quarter combat to large open-scale battles. Lighting and environment cover all times of day, as well as a specialized infrared night vision mode that required extra performance budget. Furthermore, Call of Duty Warzone, a free-to-play massive 200-player first-person shooter based in Modern Warfare world, utilizes the same engine, reaching unparalleled player count in vast open world at 60 Hz. Call of Duty Warzone stretched the engine to the limit. Therefore, we started looking towards new ways of optimizing our rendering performance. I would like to introduce you to hardware variable rate shading. Hardware variable rate shading is a new feature introduced in DirectX 12 Ultimate. It's supported by all HVS at the moment. AMD GPUs supported from RDNA 2 architecture and up. Intel supports Gen 11 APUs and up. And NVIDIA supports Turing GPUs and up. Variable rate shading divides into two tiers of hardware support. Tier 1 allows you to set shading rate per draw call, whereas Tier 2 allows to set shading rate per screen tile or other frequencies at a minimum size of a tile of 8 by 8 pixels. The idea behind variable rate shading is somewhat simple. The hardware allows to pick a shading rate that's appropriate to image frequency of the image that you're seeing. So if the image being rendered doesn't actually have too many details in some kind of region, it allows you to render it much faster. Call of Duty already has a history of variable rate shading in previous titles. Call of Duty Infinite Warfare and Call of Duty World War II already used a form of VRS. The previous engine used software-based implementation of what would be VRS Tier 1 in DirectX 12. We allowed our artists to set materials to render at full resolution or half resolution, so it worked on a per draw call basis. The primary use case was multi-resolution VFX rendering. We also allowed certain transparent types of geometry to render with multi-resolution, like glass or visors. So in the end, it was fully controlled by artists. In this screenshot, you can see a typical scene from Infinite Warfare with very heavy VFX paths. As you can see, it's taking 5 milliseconds to render all the VFX that you're seeing. If we would lower the VFX resolution to half resolution, performance gain is quite significant. From 5 milliseconds it goes down to 2.4 milliseconds. Unfortunately, several VFX types take a massive image quality hit, such as sparks in the background. Those were deemed unacceptable by our VFX team. So we basically had to develop this multi-resolution technique to cater to those situations. Here you can see a multi-resolution rendering mode where we run at 2.8 milliseconds, and the sparks and other high-frequency effects are rendered at full resolution matching and mixing correctly with half resolution rendering of other smoke and fires. If we were to compare that to a reference image, we can see there's barely no difference, just a very significant performance gain. So let me first introduce you to our old multi-resolution pipeline that was introduced in previous title. First, we start with depth stencil prepass. Depth stencil prepass produces a standard classic depth buffer that's later used for all the opaque forward plus rows, and those generate a standard color buffer. But then there's also a compute job that reads the standard depth buffer, decompresses it, downsamples, and swizzles to a 4 times swizzled MSAA depth buffer. We also generate the high Z tile information to accelerate the hardware. This depth buffer, the swizzled 4x MSAA buffer, is used by all the VFX and transparency for blast rows. And those generate a 4 times MSAA swizzled color buffer. Finally, there's a merge, deblock, and interpolate pass that reads both color buffers and generates a final blended image. That image is passed to post effects and to final temporal anti-aliasing. So what we've noticed with this solution was a 3x to 3.8x performance scaling on all the material stack for low resolution rendering. There was a fair amount of variance that depended on the render target microtile hit and overlap between full res and low res particles on screen. The actual cost of upsample, resolve, and reconstruct paths was varying between 0.3 millisecond to 0.4 millisecond combined, where the variance came from an amount of microtiles that needed to be subsampled. You can check more numbers in the original presentation from 2017. However, I would like to notify that mileage may vary depending on your GPU MSA efficiency. And the final thing was that we had a lot of concerns with quad occupancy on certain high triangle transparent rows that we're gonna get back in the future slides. So after this success, moving to the next project, we decided to start a new experiment. We already had a pipeline set up similar to VRS Tier 1, so we could change sampling rate on per row basis. So the experiment was what would happen if we would actually render the whole game using 4 times MSA swizzled buffers. So basically at half resolution to match the original resolution target, but with 4 times subsampling. So that's exactly what we did. We set up 4x MSA buffers, depth and color, and we allowed each draw call to render with 1 subsample, 2 subsamples, or 4 subsamples. So what we observed, and what was kind of a clear win, was a massive speed up to prepass rendering, especially foliage, where basically the minimized wavefront counts and more efficient alpha cut-down due to combined SV coverage output was a huge gain. In terms of flexibility, this setup was matching DirectX 12 VRS Tier 1. However, when we actually look at the performance counts, we can see that not everything is looking that great. So first and foremost, with no MSA rendering, just standard scene rendering, we're looking at 18 milliseconds. When we allowed our artists to manually tag objects in the scene, we ended up with about 17.26 milliseconds. It required a lot of manual work, and the image quality didn't always hold up in all the distances. Then, if we were actually trying to run the game at the same quality as no MSAA, we ended up actually running slower than no MSAA mode, even though we put a lot of effort into this. The image quality was obviously the same as no MSAA, however, the performance was lower. Then, trying to run the game at 2 subsamples, we noticed that we're running only 1 millisecond faster, but that there was a visible loss of image quality, and the performance gain was just not high enough to compensate for the image quality loss. And then finally running everything with 1 subsample, 15.3 millisecond, it was a pretty decent performance gain. However, the visual quality was just unacceptable. So we need to ask ourselves, why did it fail? In a lot of our captures, we found one draw call that was especially problematic that nicely shows the problem. So this draw call is a draw call showing a rendering of a full forest. It has 132,000 surviving triangles that generate 886,000 surviving pixels. That gives us a rough ratio of pixel to triangle count of 6.7. So if you know your hardware, you know that this is not going to be an efficient row by any means, even if you don't use MSAA. So let's look at the numbers. If we render this row call with no MSAA, we're looking at 0.9 millisecond and generating about 42,000 compute waves. And that generates about 900,000 pixels. If we would normalize this time to 1 megapixel, we're looking at 1 millisecond. Then when we switch to MSAA and use all 4 SAP samples, our time goes up to 1.3 millisecond and staggering 1.46 normalized time. The reason for this is that we're generating so many more waves for pixel shaders and still generating pretty much the same amount of pixels, which means that the GPU gets less and less efficient. And we can see this loss of efficiency when we switch to 2 SAP samples and 1 SAP sample. Fortunately for us, there's a linear scaling when MSA modes are enabled, but the big gap is between actually not having MSAA and enabling MSAA. So in the end, we can see that the GPU forms more pixel waves for roughly the same amount of output pixels, and this results in very significant rendering inefficiency. So we need to get back to the drawing board and refresh a couple of concepts about rasterization and quad occupancy, MSA interactions with quad occupancy, MSA interaction with memory, and stencil interactions with MSA and quad occupancy. While doing that, there's going to be an additional subject about interleaf rendering, which is a concept of optimizing a lot of non-cache efficient rows and jobs. So first, let's focus on the rasterization and quads. Rasterizer generates pixel quads if a triangle intersects at certain sampling points. So let's say if a triangle is going to be intersecting a sampling point inside of a pixel, it's going to mark that pixel as a sampling point that needs to be generated. Then when all the samples are marked, a hardware piece called TileWalker and Wave Packer is trying to form a pixel shader wave. It basically tries to find all the live triangle quads from a 32 by 32 super tile. If there's a thread from a quad that's actually missing, it's going to be generated as a helper lane. So let's say if we actually have a single sample right here that hit the triangle, we still need to form a quad for it because quads are what the GPU uses to calculate derivative calculations. So for a single sample like this, the GPU would actually still generate 3 additional helper lanes, threads that the only purpose is to actually aid that one thread in trying to find the derivatives. It's also not necessary if we're actually looking at a single quad that's inside of a triangle. In that case, we're looking at a really high efficiency. So quad occupancy is a metric of pixel shader efficiency ratio, basically amount of pixels rendered divided by 4 times amount of quads formed. One thing that's not worth noting is that compute shaders have no support for such packing. So in this case of a single triangle rendered at this resolution, we will be looking at 3 waves and 9 quads being rendered. We mostly focus on quads because when rendering images, we're just having hundreds of thousands of quads, and those get packed in the waves. But what's most important for us is amount of quads. So how does the quad occupancy and resolution interact together? Let's say we're rendering a triangle at some kind of given resolution like in the previous slide. In this case, we're looking at 25 pixels that are actually worth something. That means that those pixels are the pixels rendering that triangle. Those 25 pixels are going to end up generating 9 quads and split between 3 different waves. So our quad occupancy ratio is going to be 25 to 9 quads times 4. That means about 69% of quad occupancy. If we were to drop the resolution by half, we're going to see that we're actually rendering way less pixels, but there are going to be way more sampling points. They're going to be falling close to the edge of the triangle, which means that a lot of quads are actually going to have missing samples. So for 6 pixels here, we still need to generate 3 quads, even though those are going to be in one wave. But if we look at the quad occupancy calculation, we can see that the quad occupancy is much lower than at higher resolution. Even though we render less pixels, we render them less efficiently. Then comes MSAA. So multi-sampling anti-aliasing operates in something called color planes. Basically, every quad is generated for each plane individually to allow correct derivative calculation. This means that enabling MSAA drops the virtual resolution and hence it's going to lower the quad occupancy. So if we have a triangle rendered over a 4 times MSAA grid, we're going to be generating quads in 4 different planes. And those planes, in most cases, at least on AMD GPUs, are going to be swizzled between each other. So every quad of the original image is actually going to get one subsample, and those subsamples are going to form actual quads, but from individual planes. So in this particular case, when using MSAA, and we ending up with quad packing of them, we would end up with 25 pixels in 13 quads, generating 4 waves, at a quad occupancy of 48%. This is actually lower than the original rendering that we were discussing a slide ago, because we're at 69. And as you can see, it's actually almost matching the quad occupancy of half resolution rendering. It was 50%, with MSA it's 48%. So another question we like to ask is, how could we actually kill certain samples and still get a performance benefit? Stenciling is a hardware feature that allows us to kill individual samples. However, a single sample kill won't result in any performance gain due to helpful threads in a quad. So in order to kill a quad, we actually need to be stenciling out all the samples. In a non-MSA rendering, this would result in 2x2 missing quad. So just as an experiment, let's take our previous row call at a given resolution and take a stencil that's just a checkerboard. If we were used to a stencil checkerboard, we would end up killing every other sample in the image. So originally we were rendering 25 pixels. With a checkerboard stencil, we're rendering only 12. However, because we need to generate helper lanes for each of those samples, we still end up generating 8 quads in 2 waves. So our quad occupancy here is actually going down drastically, down to 37%, even though we're rendering, well, half of the pixels, but at much lower efficiency. In MSAA, resulting checkerboard will actually be a pattern in 4x4 blocks because the image plane, the color planes are interleaved, and thus the interleaved quads and derivatives. That means that if we were to use a checkerboard pattern in MSA rendering with stencil, we would only end up killing certain planes in 4x4 pixel quads. And that's going to result in significantly better quad packing. So in this case, we still have 12 pixels, but that gets packed to 6 quads and a quad occupancy of 50%. So again, comparing with the previous setup, we had a quad occupancy of 37%, so we had a significant loss due to stenciling. Whereas here, stenciling actually didn't change our quad occupancy at all. So with MSA, we managed to kill all samples that we needed killed, while keeping quad occupancy mostly unchanged. And triangle interior, as long as contained within those 4x4 pixel blocks, can still be rendered at full quad occupancy. And finally, we get to MSA swizzle interleave rendering. There was a concept introduced in 2014 of interleave sampling for cache-efficient sampling. The idea is that we can take a full resolution texture and de-interleave that in an array of small resolution textures, then do computations on those images and swizzle them back into a full resolution image. The gain comes from the cache efficiency, where actually running jobs on those low resolution targets can allow us to save on cache thrashing. MSAA naturally swizzles and produces interleave data right away. So this process can actually be used on AMD GPUs to significantly speed up certain jobs. Furthermore, AMD keeps color planes separate in memory for better cache coherency and allows power sampling or rendering thanks to FMAS compression. You should try to look it up through AMD docs. So many compute jobs and post-effects jobs can actually utilize interleave sampling. You could sample plane 0, assuming that's always available, or you can sample up to arbitrary amount of planes. You could also try to avoid redundant samples due to FMask. So after going back to the drawing board, we understood what went wrong with our experiment, and we got a couple of new powerful tools in the toolbox that would allow us to actually maybe make this VRS experiment work. So the plan was to still render everything with 4x MSAA swizzle, and we wanted to use stencil for variable rate shading alike masking. Our early research indicated that the negative performance loss that we noticed from MSAA could be minimized by aggressive sample rate changes, interleave rendering, and optimized compute jobs and post-effects jobs that would take advantage of VRS masking. So the primary advantage over hardware variable rate shading would be that this implementation will be available on all platforms, including current generation consoles. It could also lead to potentially higher performance due to smaller tiles, because our tiles are quad size, 2 by 2, versus 8 by 8 in hardware implementation, and potentially higher image quality due to smaller tiles and implied reconstruction methods. So, with high hopes, we try to deliver something that's going to beat the hardware implementation. Inspired by those experiments, after more analysis of fail cases, we decided to pursue implementation of software VRS throughout the whole rendering pipeline. This is an opening shot from one of our small MP maps. As you can see, it exhibits a lot of areas of high frequency details like foliage, canopies, or texture work. And there are also a lot of areas that have a lot of low frequency detail, like the areas behind the volumetrics, or the sky dome, or the shadowy parts of the screen. This image shows our VRS shading rate view with four distinct colors indicating different sampling rates. Green indicates a single sample per pixel quad, yellow is 2 samples, magenta 3 samples, red 4 samples. As you can see, those areas are matching the high and low frequency areas of the image. So the foliage and ground texture, they got red and magenta, meaning they have high sampling rates, and all the parts of the screen that were hiding behind fog or in shadow, they're getting green, which means a single sample per pixel quad. So now let me drive you through our pipeline setup. First, we have a prepass that renders primitive IDs, dep, and stencil. Additional metadata that's driven by that prepass is the fmask, which is for color buffers. In our case, it's the prim ID, 4x MSA stencil, because all those buffers are 4x MSAA, and depending on the draw call, there might be velocity buffer attached. Then there's one additional buffer that comes from the previous frame. It's the VRS image mask history, which is being reprojected every single frame. All those buffers are used by a compute job that generates and updates the history of the VRS render mask. This buffer generates the VRS compute mask with wave packing. This is something we're going to be using for a lot of our compute job. And it also generates the VRS render mask that will be used by the actual rendering, along with the 4x MSA stippled stencil. Then there are multiple compute jobs that are using the compute mask with wave packing, and actual forward blast rows that are using the VRS stippled stencil. This is followed by VRS resolve and deblocking pass that's using the VRS render mask for correct deinterleaving, deblocking, and interpolation of input samples coming from forward blast rendering. And then we have our standard post effects, followed by gradient detection. Gradient detection pass is used by our temporal anti-aliasing, but it also uses the VRS image mask to generate the new update for the mask history. Finally, all the data from gradient detection and post effects goes to temporal anti-aliasing. So the general frame setup is quite simple. We render everything with 4 times MSAA swizzle and deinterleaving in mind. That means that not only draws but also compute jobs need to be fully aware of the 4 times MSAA swizzle on the input buffers. Our VRS operates at pixel quad granularity, which means 2 by 2 pixels, as opposed to hardware implementations working on MSA tile sizes of 16 by 16 or 8 by 8 when MSA is disabled. Swizzle patterns are used throughout multiple frames. We basically, instead of standard pattern where you have a single subsample per pixel, we use 4 subsamples in a single MSA pixel. And every frame, we rotate those samples. So after 4 frames, we had 4 rotations. This is to help with temporal stability and add more detail from frame to frame. The top left pixel is always called the provoking pixel. And we want to make sure that this provoking pixel is always coherent between different subsamples that we're going to be having. Also, for the sake of this presentation, we're going to be assuming only the first pattern, which means 0 top left, 1 top right, 2 bottom left, 3 bottom right. And we also manually create the stencil mask from the VRS shading rate map to drive our forward plus rendering. Our VRS image mask is at per quad granularity. It's a 2-bit mask that's based off image data only, and we use it for image shading rate estimation as well as generation of the VRS render mask, the actual mask used for creation of the stencil stippling pattern and reconstruction. The image mask itself can have 4 different distinct modes. single sample mode, where the provoking vertex is the provoking pixel is the only one being rendered, the horizontal gradient one, when we basically detect there's more difference in the image on the horizontal axis, so we're rendering more subsamples on the horizontal axis. Same for vertical axis. And finally, if the gradients are going in both directions, we render all subsamples. One thing that's very important for the performance of our reconstruction process is that the provoking pixel is always retained in all modes. In our gradient detection pass, we use image-based local gradients to detect differences in the image. They use a series of image-based gradient codes. Basically, because those are 2-bit masks, we can easily express no gradient, direction horizontal, direction vertical, and finally sum of all directions as only 2 bits. The important fact is that we can OR those masks, and we're always going to get conservatively upsampled to all directions. When we're detecting local gradients within quantiles for VRS, we need to get some kind of threshold when the actual difference in the quad happens. For that, we're using the Weber-Fechner just noticeable difference law. It's basically a perceptual law that tells us what kind of stimulus we need with given environment to make it just barely noticeable. We use this law to detect horizontal and vertical differences, and we use that to detect the first and second derivative of those aforementioned gradients. And finally, we want to OR all those codes in pixel quads. So we calculate it per pixel, and then we OR that within pixel quads. In order to calculate the local Weber-Fechner K factor from the law, where we actually need to know what's the stimulus threshold, we calculate the minimum of the local block of pixel luma. Then we max it with the device black, where the device black is your output device, and multiply by somewhat arbitrary VRS quality threshold. That VRS quality threshold means how many percents of the stimulus we allow to be just noticeable or basically unnoticed. This is when the VRS is going to kick into higher gear, rendering more subsamples. The actual gradient detection is very simple. We detect the horizontal gradients by taking the maximum of absolute differences of colors with a single pixel difference, and for the second order with the 2 pixel wide span. And then we take the maximum of both gradients. We repeat that process for vertical differences, and finally we just threshold them and we OR them. In order to get the data for pixel quads, we need to OR data, the image codes from each pixel. We can trivially use the DX and the DY operation to get it in the pixel shader, or we can just do it manually in a compute shader. So this picture represents gradient with a 2-bit image code. So those values go from black to white here, representing amount of subsamples that we would be using. As you can see, all the areas of high frequency details like grass are getting a lot of samples, whereas places are quite flat in terms of image, getting way less samples. And those correspond to our image-based gradient codes. Then in any kind of motion, there are going to be multiple sources of signal loss. There's going to be aliasing coming from temporal coherency of objects and scene elements. So basically when the camera is moving or panning, things are going to be moving between frames. There's motion disocclusion, meaning there are going to be new pixels that were not visible in previous frames, as well as jitter that might be coming from different algorithms like temporal anti-aliasing or other temporal algorithms. That means that our VRS rate prediction relies very heavily on temporal coherency of gradients. And as I said, there are multiple sources of aliasing and data loss, and we need to find ways to stabilize them over multiple frames. There are a couple of proposals of using spatial smoothing and motion compensations functions to somewhat stabilize the data. However, those are very targeted approaches that require a lot of tuning and might result in overestimation. In our case, we focus on conservative temporal accumulation and prediction. So let's take a look at several frames of gradients as 2-bit images. This is frame N. Next frame definitely shows new details. It brings more gradients, and that's because of the camera motion and our temporal jitter. Our temporal anti-aliasing uses 2 or 4 frame long jitter sample rotation patterns. Thus, 4 frames should be enough to capture majority of non-motion induced high-frequency data fluctuations. And it becomes clearly visible that estimating future shading rate is impossible using only a single history step. because each frame adds more high frequency details, thus it should be taken into consideration during the final estimate. To avoid temporal instability and data loss, we explicitly hold last 4 frames worth of gradients in memory. Each frame should be correctly reprojected. To minimize the performance and the memory cost, we decide to store all frames in a single buffer that will be continuously reprojected and rolled to refresh each frame. Considering we use 2-bit gradients, this can be trivially achieved by bit shifting an 8-bit buffer by 2 bits with every update. This way we achieve a FIFO queue. Then the next job is going to be generating the VRS render mask. It is a buffer used to drive 4x MSA stencil stippling, as well as all needed reconstructions and resampling in multiple compute jobs throughout the frame. In order to generate the VRS render mask, we need following data: velocity buffer for correct reprojection, image mask history buffer containing last 4 frames worth of VRS mask that we just generated. We can reproject it and disocclusion cull it in one single go. And fmask that is read from prepass buffers. Fmask is used to generate VRS geometry mask, which is a auxiliary optional buffer that's used in order to finally guide higher frequency sampling on geometry edges if necessary. The actual compute job produces multiple output buffers. First, there's a reprojected 4 frames of VRS image history mask, then the VRS render mask that's at per quad granularity. It's represented as 8 bits of either reordered F mask or 2-bit image mask that's conservative over the last 4 frames. We basically try to optimize a case where there are just multiple geometry edges within the quad. If that happens, the F mask is going to be showing multiple edges. If we detect that a single quad would require a lot of image samples, and it also has a lot of geometry samples in it, meaning edges, would prefer to use the F mask if it can provide lower sampling rate. This basically follows an assumption that if there are multiple geometry edges over a small region of screen, it's probably enough just to reconstruct them instead of reconstructing the actual interior of triangles. And this seems to be very true for a lot of foliage and alpha-tested foliage, and we found this to be a very important optimization. Furthermore, F-mask is reordered in sample order to avoid indirection when sampling later in the pipeline. The VRS render mask is used purely for deblocking and reconstruction. The code for generation of it is provided in bonus section. Another output from this compute job is a 4x MSA stencil update to the stipple render pattern. It stores directly from VRS render mask. Because we need to write to the stencil target, we have to do it manually by manually aliasing the buffer as an unsigned 32 image and writing to it according to macro tiling of the texture. This is something you would need to look up with your GPU provider. And then the final output is the VRS wavefront packing buffer, which is at pixel granularity. And this is an auxiliary buffer that's going to be used by a lot of our compute jobs later. Let's move to software VRS draw setup. In prepass at very least, you need depth and stencil. Fmask is highly recommended if you have any other targets already. Call of Duty Modern Warfare uses visibility buffer compatible prepass with 32 bits worth of depth, 8-bit stencil, and 64-bit auxiliary buffer with primitive ID, velocity, normals, and other data pieces. For optimal setup, use 4x MSA swizzling with color compression enabled. Make sure that pixel shader iteration count is set to 1, and set interpolators to use per sample interpolation mode in order to precisely match sample positions with regards to original non-swizzle target. Prepass performance will be significantly improved, which can be a huge boost for visibility-style rendering buffers where only per vertex data is needed. Later, per vertex data can be trivially interpolated from MSAA samples. You need to pay extra attention to all the draw calls that have alpha testing. You need to output manually the SV coverage mask. Coverage mask needs to be evaluated exactly at sample positions, and in order to do so, we need to manually calculate subsample alpha test results, concatenate them, and output into SV coverage mask output. This piece of code provides guidance on calculating those samples. So basically, first we need to get our UV coordinate derivatives over x and over y. It's important to remember about the scale on them. In MSA setup, your gradients are going to be twice as large as they would be non-swizzle rendering, so we need to multiply them by half. Then we have something we called the derivative offset mask, which is generated with regards to provoking sample. So basically where the UV is interpolated at. This mask needs to provide data on how to offset the UVs to generate each of the subsamples. So in the most general case, when the provoking pixel is the top left one, your DD offset mask for first sample would be top right, then bottom left, and bottom right. We calculate our subsample UVs, we sample our opacity or any other map that used for alpha testing, we do thresholding, and then we are with our coverage mask. And finally, after iterating through all the samples, we output the coverage mask to SV coverage. This image shows a typical high foliage overthrow seen from one of our MP maps. And here you can see a comparison between non-MSA prepass and the MSA prepass for aforementioned scene. As you can see, the MSAA with manual SV coverage unroll results in significantly less waves. So basically, those waves that you can see here are from the alpha testing. You can also see that a lot of them are actually waiting on expert allocation, which means that they're spamming our render targets. Whereas here in the MSAA case, with manual SV coverage, we see that we're issuing less waves, and those waves end up less time spamming the render target output. And this results in significantly higher performance. If we look at two different scenes that show different setups, in one we have heavy alpha tested overthrow, and the other one shows a typically well balanced scene between different geometry types. We can see that the VRS prepass gives us quite significant gains. In terms of heavy alpha test overthrow, we can see a total saving of 29% and diminishing 20% in 1 megapixel. Then in a more typical scene, 2 megapixel image is gonna give us about 11% gain, whereas going down to 1 megapixel is gonna give us 5% gain. MSA prepass also results in a lot of bandwidth improvements for compute jobs. Depth and standstill decompression jobs are significantly faster. We also noticed that you can save a lot in velocity normal or primitive ID resolves if you're using the fmasking direction. There are also many algorithmic optimizations possible with sparse sample compaction. Furthermore, lower resolution passes can just read out plane 0, which is implicitly given, to cut memory bandwidth by 75% and sometimes even bypassing the fmask. If we were to look at our passes, we're gonna see that there are significant gains. On PS4 at 1080p, depth decompression and depth pyramid pass goes down from 0.45 millisecond to 0.25 millisecond, which gives us a 44% gain. Then primitive ID processing, which gains a lot from algorithmic optimizations, goes down from 0.2112 to 0.072, which gives us a 43% gain. And then velocity resolve, which is kind of bandwidth limited, goes from 0.11 millisecond to 0.1 millisecond, giving us a 15% gain. Proposed compute shader improvements involve generating a working queue of samples in LDS by grabbing and compacting all active samples from fmask. So what we do first, we iterate for all the planes, and we get our MSA sample index from fmask, and we concatenate that into a binary sample mask. Then we want to create a queue when we're going to be uploading individual samples from each of the planes. So again, we iterate for all the planes, and for each lit bit from the sample mask, we're going to ballot it over all the active waves in the wavefront, producing a producer mask. This mask basically tells us which thread for current sample plane is active. If it's active, we're going to generate a local queue offset for it by using compaction from mask bit count. And then we're going to be uploading our data to working queue. So the work queue is an LDS queue where we basically store our data that's loaded from any kind of MSA texture. In this particular case, we're just loading the triangle ID. Then we upload the queue, offset it, and iterate for all the planes. Then the queue can be iterated by rolling wave-long batches within a single compute shader wave. So obviously we need to flush the LDS queue, and then it's enough to have a while loop that goes in wave-size batches over data from the queue. So every thread for every iteration is going to be loading its own compacted offset to the queue, loading it, and then you just need to process whatever kind of data payload you have. This allows you to significantly optimize sparse sampling in your compute jobs. When it comes to actual opaque throws, there are a couple of things to remember about. Color buffer needs to be set to disable fmask compression. This is somewhat important because fmask in this particular case is not actually going to be helping us at all because we don't know what's going to be expected amount of subsamples. Worst case, we're going to be rendering all the subsamples, so fmask is not actually going to be doing anything. So using fmask in opaque throws actually adds unnecessary bandwidth and memory cost, and it would also significantly complicate all the image results. Stencil needs to be set to a stippled stencil value from the VRS pass, and there's no alpha test set in any of opaque throws. We basically just use def equal equal. Then you also need to remember about using per sample interpolation, and you also need to make sure that your texture sampling is matching non-swizzle rendering. In order to do that, you need to remember the biasing your texture samples. So use sample bias and bias it by the difference between your non-swizzle and swizzle targets. In the discussed example, we're basically talking about -1 because it's just one step of a difference on x and y. And you also need to manually correct derivative calculations if you ever use them. So if there's any place in your pixel shader code when you're using the results of ddx or ddy, you have to remember to basically multiply them by half in this particular setup of for x MSA swizzling. So now let's observe different planes and how they react with different subsample stencil cutout patterns. So color 0 is the plane 0 of our MSAA rendering. Stencil 0 represents our provoking pixel, which is basically always lit. Then when we look at our first subsample, we can see there's only a handful of lines that are following the horizontal gradient in that case, and have some additional detail where necessary. And now you can see color samples. So as you can see, color sampling, generation of pixel shader invocations for the second color plane is actually quite sparse. We can also see that it's precisely matching all the edges of all the geo. And then we can observe exactly the same thing for each plane, for plane 2 and plane 3. So each plane captures high-frequency features relevant to that sample location. Another important step in our pipeline is image reconstruction. Let's inspect VRS image quality. Looking at this test render, we'll focus on two areas that might not be immediately obvious to show differences between hardware VRS and software VRS with image deblocking enabled. This image shows hardware VRS, and this shows software VRS deblocked with region of interest marked red. If we look closer, it becomes clear that non-deblock areas have subpar image quality, looking like naive nearest neighbor upsampling, whereas deblocking looks like bilinear upsampling, retaining all the low-frequency gradient information correctly. Another comparison shows the same visual discrepancy. It's worth noting that such artifacts can become extremely distracting in motion because those artifacts are VRS sized, 2 by 2 pixels at least. Thus, in most cases, they will fall from most temporal anti-aliasing implementation. When VRS resolve and deblocking happens, we need to read VRS render mask per quad, decompress, and resolve different interpolation modes. Decompression and resolve depends on the quad type that's stored in the mask. As we discussed before, the render mask can store either fmask for more geometric-based resolves or image mask for image-based resolves where a correct interpolation mode needs to be picked to avoid blocky artifacts. One important thing to remember is that interpolation of samples outside of the quad subsample might need a neighborhood check, because samples outside of your quad might not actually exist, so you would need to check their own software VRS render mask for them and fall back to some other subsample. Piece of code here illustrates this problem. So we load our first subsample, which is the provoking pixel and is always available, and then we iterate through 3 additional subsamples. They're going to be loaded from the MSA texture via load, and we need to provide which sample to actually load from it. But before we do that, we need to load software VRS mask for each of those subsamples. And then we call getValidSampleID, which is a helper function that takes software VRS mask as input and sample ID that we're looking for. Internally, we need to take our software VRS mask and transform it into a bitmask representation that tells us which samples are actually available. And then it becomes a trivial bit field offset check and grabbing first bit low in case that sample is actually non-active. In this case, we would just fall back to the first available subsample. And here you can see an example of patterns and their reconstruction. So in case of a one sample per quad resolve, we'll be resolving its neighborhood on the right side, top right, from two nearest provoking pixels. We do exactly the same for vertical subsamples, and for the final third subsample that's on the diagonal to the provoking pixel, we might as well just take the whole neighborhood of four nearest provoking pixels. Then in the case of two samples per quad, we have to do a resolve horizontally or vertically. In case of horizontal resolve, we would just grab two nearest subsamples for each of the vertical subsamples. And we do exactly the opposite for the vertical resolve. First sample resolve is somewhat trivial, so it doesn't need any kind of discussion. Then complex reconstruction can be pre-computed, in example, using machine learning approaches for best reconstruction pattern and weights. This is somewhat similar to method presented in coverage reconstruction anti-aliasing. Neighborhood patterns are gathered and ORed as a single lookup to a lookup table that contains reconstruction codes. Then a sampling and weighting loop uses reconstruction code to pick correct samples to blend at their most appropriate weight. Search space for this can be somewhat large, with each neighbor represented by 2-bit mask. With a 3x3 neighborhood search that gives us 18-bit long hashes, which is still somewhat reasonable for an exhaustive array lookup. Payloads needs to be at least 8 bits long, 1 bit for each neighborhood sample, and weight control could be added at the cost of more data. One way to minimize the space is to exploit quadrant subspaces with regards to sample being computed. So in this case, we would be looking for the quadrant of the nearest quads that would contribute to the subsample we're interested in. So in this case, each sample from an active reconstructed quad would have its own subspace considered for reconstruction. So in this case, we would be minimizing the lookup space from 3x3 to 2x2, thus down from 18 bits to 8 bits. In 16Hz Call of Duty title, this whole processing adds a bit too much of an overhead versus naive base patterns that were presented on the previous slides. We might revisit this later, although we didn't spend too much time optimizing it for our title. And finally, we get to the last stage of our VRS pipeline, that is, optimize compute shader jobs. Full-screen passes generate data consumed by F+ rows. Those will contain unused pixels if waves are not compacted correctly. Compaction in pixel shader happens via tilewalker and wavepacker, and those are the units that allow our third plus opaque rows to actually gain any benefits from the VRS pipeline. On the other hand, compute jobs have no support for such packing, therefore we need a software solution for them. One idea better than brute force evaluation of all samples is to iterate active subsample planes. This can be achieved using dispatch indirect path that requires preprocessing and issuing step. In this case, for each 16x16 screen tile, we would OR active subsample planes in all quads, issue as many waves as lit bits, and we would also have to store 2-bit ID in a per wave buffer so each wavefront could identify its own position within the 16x16 tile. Eventually, one could use dispatch and resolve wave iteration within the shader itself. In this case, a single wave would roll multiple times. This code snippet shows how to do it. So first, for every thread, we would load software VRS mask. We would get the valid sample mask for every thread. And then we would use a crossline operation to OR all the masks, creating a wave unit for sample iteration mask. And then it's just a matter of iterating the whole sample iteration mask until all samples are exhausted between all the planes. This naive plane packing scheme will allow us to minimize amount of dispatch wavefronts to maximum of different planes found in all the masks. In testing, we found out that long waves that roll can sometimes stall the pipeline if there is high divergence in iteration count. Considering that we have multiple compute jobs that share same tile prepass, we decided to focus purely on indirect path approach. This image shows a software VRS mask per quad sample count. white indicates 4 samples, levels of gray 2 to 3 samples, and black 1 sample. As you can see on the next image, using dispatch indirect plane iteration method is very far from ideal. Because of our packing scheme, we need to dispatch a wave even if there's just a single subsample out of a plane. This results in a very low efficiency, especially in noisy images where sampling pattern can change often. Another idea is to use wave compaction. This scheme for wave packing will allow us to minimize amount of dispatched wavefronts to sum of all items modulo wavefront size. In this case, for each 16 by 16 screen tile, we would have to calculate all tile workloads. So if we are looking at an arbitrary GPU with a 2 by 2 wave size, then each of those tiles is composed out of 4 waves. We would have to count how many threads we have active per each wave. And then we would calculate additional buffer that stores wave rolls per tile. So in this example, we can see that the first tile would require 2 full waves to roll. Second tile would require 3 waves to roll, and then 2, and finally 4. The last one is 4 because it only has a handful of samples missing. So then we would have to iterate all quads and order them via subsample ID. So we basically try to get all the subsamples ordered and pack them tightly in waves. And packing them one by one, we end up with ordered planes corresponding to each of the original plane in a new wavefront setup. We'll basically need to store blocks of 64 thread worth per thread offsets within each 16 by 16 block. This can be trivially encoded by 4-bit X and 4-bit Y coordinates, and per wave iteration count in 2 bits. Then we would have to dispatch compute shader waves, and they would have to look up their wave ID and look up per thread offset blocks with wave ID. Then, one additional optimization is a direct consequence of sample ordering and the fact our sampling pattern always guarantees existence of sample 0. Therefore, there is no need to store first wave offset map. Also, in a case of 4 waves rolling, there's no benefit of repacking, because however tight we pack, we still need to run all 4 waves. This piece of code is somewhat more complex than the previous one, so I highly recommend taking your own time looking through it. But just going very briefly through the overall structure of code, first we would need to grab all of our subsample maps for all the threads. And we would calculate the sum of all of them over all threads active in the wave. Then knowing how many subsamples we actually need to roll in each of the wavefronts, we would decide if we need an extension of the thread offset maps if our wave rolls are over 1 and below 4. In this case, we would just load up our LDS queue, kind of like we already did previously in one of our examples, this time loading it with item location, where each item is basically a thread offset within the tile size of 16 by 16. Then we would flush our data to the queue, and then for each of those 2 planes that we were just right packing, we would output them in a compacted fashion, writing out 2 planes worth of VRS tile packing buffer. And then finally, for each of the tiles, we would just output a single tile subsample wave count. So we would know how to actually unpack those tiles. Then the indirect dispatch shader would read the VRS tile mask itself. It would calculate the local thread offsets for indirect dispatch using tiled exclusive prefix sum. And it would also calculate how many unrolled items we actually need to shoot. That means how many wavefronts we would be issuing. If there are any wavefronts to be issued, we would up our indirect argument buffer, so we would actually issue more waves. And then, for every wave that would actually fall into the category of being fully unrolled and reading the tile offset map, we would pack some auxiliary data into a per wavefront buffer. That auxiliary data would contain whether the wavefront is packing enabled, its own wave ID, and thread offsets. And then we would just shoot them off. Then when actually using this kind of shader, we would read a 16 by 16 tile data worth in an execution tile of 8 by 8. For each of the wavefronts, we would need to identify it by reading its own data. From that data, we would know if the wave is actually having packing enabled, we would know its wave ID and its wave position within the tile. Then, if packing is enabled, we would have to read the additional VRS tile packing buffer using the wave ID. And from that, we would get the tile pixel position within the actual tile that we packed previously. In case if packing is disabled, it would be just as simple as passing through the wave internal pixel positions and moving them to the global tile of 16 by 16. At this point, we can just get the final screen coordinates that we have here and just do something for sample. So how does it fare? Just as a reminder, let's look again at our software VRS mask per quad sample count. And as a reminder, this image shows the SVVRS mask per wave sample count after using dispatch indirect plane iteration method. And now we're looking at our SVVRS mask per wave sample count after using dispatch indirect plane wave compaction method. It is clear that this packing scheme is significantly superior. It's actually matching pixel shader hardware implementation, although at a smaller supertile size. As already discussed, our scheme operates at 16 by 16 tile size, where most GPUs pack pixel shader waves from larger tile sizes. Although, one could trivially extend our scheme to larger tile sizes at higher memory costs for wave offset maps. And this is the wave compaction map. Each visible block shows encoded individual thread offsets within each group. Blocks that are visually close to filled gradients shows waves that are mostly fully filled. And skewed or mixed blocks show waves that were packed from multiple tiles. The darker the color, the less threads will execute within the wave. So what about performance? If we look at one of our most expensive jobs, that is sun visibility job, we can see that those methods allow a significant reduction in wave counts. If we would be using dispatch indirect with mostly naive all sample calculation for a 1080p image, we would end up issuing 32,000 waves at a cost of 0.77 millisecond. Using the naive plane iteration method would help us a bit, and we would issue 2,000 waves less, resulting in 0.7 millisecond. However, using wave compaction in such a complex scene would result in further reduction by 6,000 waves, which would result in a final time saving of about 25% versus the all sample method. So it's definitely worth using this method for a lot of very complex compute jobs. One, I have to remember that if the compute job itself is extremely fast, the cost of unpacking waves might actually be higher than calculating all the subsamples, so your mileage may vary. However, for very expensive compute jobs, this packing scheme totally makes sense. Now that we managed to get through all the steps of our VRS pipeline, let's look at some performance numbers. Let's start by analyzing this particular scene rendered at 4K on one of our high-end platforms. Even though it's overall in dark tones, there are multiple spectral reflections on all surfaces, and multiple high-frequency details. It has also been tuned for HDR TVs, thus black levels are actually supposed to be visible. Unfortunately, this presentation is in SDR, so don't mind crushed blacks. Now we switch VRS on. Enabling VRS is virtually indistinguishable. Slight tonal variation in volumetric is unrelated to VRS. So let's look at exposed image difference. This is one EV exposed image difference where we can only see a single difference on some specular edges. If we do a 6 EV exposed scene difference, we can start seeing more of the diff, but still mostly visible on specular edges and some tiny specks around. Everything else remains within the scene limits. If we look at the VRS shading rate view, we can see that the shading rate distribution is really good. Just as a reminder, green is 1 sample per pixel quad, yellow is 2, magenta 3, and red is 4 samples per pixel quad. As you can expect, walls, brick walls, and the floor that has a lot of spectral reflections are getting significantly more samples. The same can be said at the building in the back. If we look back to the main image, we can see that there's a foggy area in the middle, and that area gets only a single sample per quad. Then dropping the resolution by half using our dynamic resolution scaling results in less efficient quad distribution. VRS quads need to be promoted to higher sampling rates more often in order to maintain similar image quality. So you can start seeing that there's more and more red in the scene. Then the effect of efficiency loss is clearly visible on lower resolution platforms, In this case, we're looking at 900p. You can see the difference is actually quite staggering at this point. And then dropping further using our lowest dynamic resolution scale step shows even more drastic loss in efficiency. So what would be interesting is to see how this scales, how this whole VRS with dynamic resolution scaling scales between different dynamic resolution steps. So this comparison shows a significant diminishing performance return with lowering resolution. The effect is not that apparent in high triangle count screen regions like the view model, where the VRS initially didn't show such big gains. So you can see the view model, this is our weapon that has a lot of triangles per screen tiles, is not actually getting that much of a benefit from VRS, this is the line up here. Then looking at the scene itself, we can see that we start up pretty high, this is almost a 4 millisecond difference, but it starts diminishing quicker than not using VRS. For the whole frame, we still have a benefit of faster compute jobs, minimized bandwidth, a lot of other benefits. So the initial difference is actually really, really high. For 4K image, this is more than 5 milliseconds. So now if we look at the actual table, the table shows different resolution steps going between 0 and 15, where 0 means 100% of our 4K resolution, and 15 means 50% of 4K resolution. We can see that the scaling has diminishing returns. So at step 0, it's a staggering 20%. So this is a great performance gain. But throughout the resolution loss, it goes all the way down to 13% of a gain. So it's still pretty decent, but it's definitely a far cry from 20%. So now let's see what happens if we move to one of our low-end platforms that runs at significantly lower resolution. So this comparison shows an even more diminishing performance return with regarding to the resolution and with regards to 4K resolutions. And again, the effect is not that apparent in high triangle count screen regions like view model. So again, the VRS starts a bit higher, then it's diminishing much faster, same pretty much everywhere. So looking at the actual numbers, we start from a high level of 9%. We're talking about 900p here. So we have a 9% solid gain, and it goes all the way down to about 4% gain for the full frame at half resolution of 900p. So the gains are still there, but they're definitely not as prominent as in 4K scenario. So for a couple more comparisons, let's look at some other examples here that are maybe a bit more varied. This is likely our worst case scenario due to increased quad occupancy from foliage. And also it's very, very noisy. It has a lot of high frequency details. So at 1080p on PS4, we're looking at 16.5 millisecond scene with VRS disabled. Enabling VRS wins us back 1 millisecond, so it's still pretty good even in such a complex case. That's definitely the worst case for VRS. Then looking at another example, which shows mixed lighting conditions in the scene, a lot of models, a bit of outdoors. This is actually a fairly decent scene to be kind of like a default performance benchmark in modern warfare. All details are also very well seen between light to dark transitions. Everything is very well preserved in our VRS mask. You can see very clear VRS higher shading rate on signs on walls. There's also the transition between light and dark. This is all very well preserved in the VRS shading mask. So how's the performance? With VRS off, we're looking at 15.65 millisecond. Enabling VRS shows clear gains of about 2 milliseconds, so this is a pretty good win. So what is more interesting to us at this point is what happens if we would actually change the tile size from 2x2 to something larger to potentially emulate how hardware VRS would fare with the same settings as our VRS. So going from 2x2 to 4x4 and 8x8, we can clearly see there is a significant degradation of efficiency of our method. Like it's very clear visually. So let's look at the numbers. If we look at the view model, which is already a very high triangle count part of the screen, and we know it doesn't actually benefit that much from VRS, we can actually see a loss going from 2x2 tile to 8x8 tile by almost 0.25 millisecond. It's even more prominent in the scene itself. But when we look at the percentage, we're looking at a loss of 8% and a staggering 20% of a loss. So the performance is very quickly diminishing with larger tile sizes. And this further indicates significant advantages of software VRS over hardware implementation due to smaller tile size. In conclusion, we managed to show that our VRS pipeline can remain extremely efficient and is never actually at a loss. That said, there are still a couple of future developments we would like to discuss. Let's focus a bit on interaction between VFX and opaques in rendering. VFX often occlude large portions of opaque objects. Then our VRS mask is derived from gradients after the VFX. So naturally, the shading rate map is going to be reflecting that. So opaque naturally is masked and renders at lower shading rate when it's occluded by VFX, which is pretty good. But then what's worth noting is that VFX reuses the same mask as opaque. Looking at a different scene where we can see that the VFX are barely visible, we see that they actually render at really heavy overthrow. But because there's not much of a difference between the image after rendering opaque and after rendering transparency draws, we know that the VFX are going to be reusing the opaque mask, and opaque rendering shows a lot of high frequency details. So what happens is that VFX using the VRS mask often render at a very high shading rate, even if they're perceptually unnoticeable, like right here or there, eventually in this part of the forest. So basically, we're looking at high frequency rendering in opaque throws that forced the VFX to also render at high shading rates. So what could we do with that? We could try separating the VRS from VFX and use a history transmask. It's basically a mask that is a luma difference between opaque throws and transparent throws. It was already introduced in our temporal anti-aliasing talks by Jorge Jimenez. So we could use the history mask of the trans mask to derive imperceptible VRS rate for transparent objects. Unfortunately, it would need an off-screen target because there's no way to fill holes due to our software VRS stencil culling. In case of hardware VRS, one could actually just use the different mask and duplicate the samples, which is basically what the hardware is going to do for you. Some other future developments we're interested in is dynamic VRS, where we would be basically preferring shading rate scaling over resolution scaling because it improves our silhouette preservation over far distances. Then we would like to enable more post-effect steps to use VRS. They have a high potential to scale better than dynamic resolution scaling. And then we would have to move the D-block and final resolve after post-effects. Another big thing that we're working on is making our temporal anti-aliasing resolve aware of VRS. This way, our TAA would be able to use subsamples from VRS directly, and we could skip the whole deblocking pass. This has a very high potential for yielding very good results, better than we have right now in terms of image quality, and actually be faster. Another interesting part of our pipeline that we're working on is trying to switch low quad occupancy draws to deferred style rendering. By default, deferred methods avoid quad occupancy problems in the way how they operate. So we would like to analyze tiles and use mix of stenciling and indirect dispatch to split them based on efficiency. They would go either forward rendering or visibility buffer deferred rendering. And then finally, it's kind of like a minor thing, we would like to switch our dynamic resolution scaling to work with uniform scaling instead of horizontal only. We are expecting higher quad occupancy from that. Now we can get to the final conclusion. In this presentation, we presented robust first-stage complex system for software-based variable rate shading, where one can pick and choose different algorithms depending on use case. We presented a setup for MSA prepass, wave compaction algorithm, VRS draw setup, as well as we propose a VRS mask post effects pipeline. It's really hard to see any downsides of wave compaction and VRS mask post effects. It would be only unadvisable in case of very fast, quick jobs, where setup costs for VRS masking and swizzling could outweigh the actual execution of the wave. Forward Plus benefits a lot from MSA prepass and has mixed results from VRS draws, where returns are diminishing with low resolution due to rising quad occupancy. Forward Plus transparency draws are as usual highly benefiting here. Deferred benefits from MSA prepass would vary depending on content, but would likely suffer due to rising quad occupancy and would not allow benefits of vertex attribute packing in MSA and interpolation. probably forcing gbuffer paths to run per sample, effectively becoming slower than non-MSA case. Supplemental forward plus transparency draws are as usual highly benefiting here. And then we get to the visibility buffer, which has most performance gains as it maximizes prepass efficiency due to pure vertex interpolation and doesn't suffer from triangle occupancy issues in opaque throws. It is likely the ideal candidate for all the presented techniques. And then finally, ray tracing. It highly depends on the implementation, but will definitely benefit from VRS pipeline to vary amount of per pixel sampling. In our case, we use VRS with ray trace shadows to vary amount of sample per tile per pixel. Then we use wave compaction for efficient ray bundle submission. So to sum it up, proposed software variable rate shading pipeline allows you to keep your resolution steps higher or target higher resolutions in general. And then it's definitely a great system for high PPI devices. That said, it ends the presentation. I also like to remind everyone that Activision is constantly on the lookout for fresh talent or seasoned veterans. And with that, I would like to go to question and answer session. Thank you.